Good evening, champions. How are you all? And I hope every one of you is doing absolutely fantastic. This is your chemistry expert Sanjaria sir, and today we will deal with the continuity part of our organic chemistry. In our previous lecture, we finished aldehydes and ketones, which was carbonyl compound. And now in that continuity, I have come up with carboxylic acid and its derivative. Somewhere in organic chemistry, I found that it has a huge importance, not in the terms of the marks or the weightage it carry. Also along with it, it is very important chapter because it's a miscellaneous chapter among all the chapters. So it contains mostly those kind of chemical reactions. Probably most of them you already have studied in other chapters, and that will be utilized in carboxylic acid chapter. So carboxylic acid is one segment and derivatives are another. Let us finish today this chapter very well, and let us start with this 12th standard class 12 chapter carboxylic acid and derivative. So we'll do the same procedure that we have done for all the organic chemistry chapters till now, that we initially go for the introductory part, then we come to their nomenclature or something related to their, what I call it, their isomerism, then preparations, then their physical and chemical properties, and the chemical property itself is the chemical reaction. Along with that, I have plenty of JEE Main Advanced PYQs and some practice problem that will keep you motivated until whole lecture. So just take out your notebook, start writing everything one by one. We have the first announcement first of all for all of you. Rather than starting this, I would like to give you one very important announcement, everybody, that we, an academy team, have conducted this all India mock test series, which is absolutely free, and those who are the aspirants of JEE 2025, they are heartily welcome. Come and basically examine yourself. Just try to analyze yourself. Where do you stand right now? What kind of quality question do you see? That will be helpful in your JEE main examination of 2025. And not that, just that, you will get the correct exactly that kind of motivation over here. It's a real exam simulation which is made JEE 2025. You also have the rank predictor that will give you the idea that what implementations have to be done apart from here. Now let us move forward. You all know your chemistry expert Sanjaria sir. Now we have introduction of carboxylic acid. So carboxylic acid, they are very priority group as far as the concern of the IUPAC nomenclature. So guys, this structure looks like this. We have an alkyl chain, and this alkyl chain is connected with C double bond OH. This group is a terminal group. First of all, you all must know this group is what? Terminal group. Carboxylic acid groups are what? Terminal group. Wherever it connects, it ends the chain over there. Its general formula is COOH. The exact representation is double bond OOH. What are fatty acids? The higher member aliphatic chains which are beyond C12 and 218. All the carboxylic acid which contain 12 carbon atom to 18 are considered as fatty acid. Then we have mono carboxy acid, dicarboxy and tricarboxy acids, in which a single molecule contains over one or more than one COH group. They are considered to be polycarboxylic acid, and dia means 2, tri means 3, tetra means 4. Like that, we have plenty of compounds in organic chemistry. So one of the example is basic acid, or we can say dicarboxylic acid is something which contains 2 COH group and also called as oxalic acid. We also have here monoacetic acid, formic acid, acetic acid, and then plenty like butanoic acid, ethanoic acid, propanoic acid, all of them. And then tricarboxylic acid is one in which more than one are present. This example is citric acid. Citric acid is one in which all consecutive 3 carbons are having COH group along with the center one having some hydroxy group. Anyways, now coming to their IUPAC nomenclature, we'll not waste too much of time in our IUPAC nomenclature. We already have come across through this topic in our previous session. You all have visited my previous session of GOC, where I taught you separately one lecture only on IUPAC nomenclature. So there we read that these group, which is carboxylic acid group, have got the first priority while naming or while numbering them. In the terms of principal functional group, it comes at the top of the list. And then we use oic acid in the name of carboxylic acid. In common name, we generally use their original names that has been originated from the resource they have been come up from. For an example, Formic acid is found in red ends which are called as formica. It became formic acid, but it's a common name. Formic acid, acetic acid, then we have propionic acid, butyric acid, valeric acid. If in the terms of fire, we call it valeric acid. But again, not so important as far as your JEE main and advanced concern. These are just names helpful in order to identify the compound, not too much important on the basis of their structures and all. But yes, IUPAC is very, very important. We all must know. Sometimes questions on IUPAC nomenclature also come directly, or otherwise it can be useful indirectly in so many problems. Methanoic acid, ethanoic acid, propanoic acid, butanoic acid, pentanoic acid, like that we can name this compound. Let us take one example from here. But before reaching to that, first of all, we must know what is the meaning of derivatives of carboxylic acid. So guys, derivatives are very simple, that we can define them in so many terms. Like one of the definition could be that those kind of compounds which are formed by removing or substituting the OH group by some another group. The another definition could be all of those compounds which upon hydrolysis produce carboxylic acid are considered as derivatives of hydrocarbon. Now take this example, and I have removed OH from here. So guys, there could be so many possibilities depending upon what can this G group be. So let us suppose this G group is some halogen. These kind of compounds are called as acyl halide, or we can call them acid halides. We also call them acyl halides or acid halides. Similarly, if I replace this X group by some OR is like this group, okay, some carboxyl group is only there, like apart from this, and these kind of compounds are called as acid anhydrides. Then we have R C double bond O OR dash. So these compound are called as, let us take this much as R dash. This is called as ester. You all know ester. And then we have R C double bond O NH2. These kind of compounds are called as amide. So believe me guys, these four are the very important derivatives, and we all know that once a derivative is hydrolyzed, it reproduces the original acid. So this is the definition of derivatives of not hydrocarbon, derivatives of carboxylic acid, right? Sir, please add session PDF. Yes, you will get the whole session PDF very soon, and for that you just need to go to the description part. We have given you some Telegram channel link. Join us and you will get your notes by there only. Now let me move forward. Then we have the next one is one question. What is present in vinegar? Vinegar is nothing but the acetic acid. So acetic acid is like diluted acetic acid is your vinegar. Correct answer should be B. It's a very general question and doesn't require any too much of information. Just an informative question, not a conceptual one. We have now preparations of carboxylic acid. So as we all know that this is how the flow of any chapter works. We initially go through the introductory parts and we reach their preparations. We have plenty of methods to prepare carboxylic acid. Right after that, we'll come to individually one by one to the all carboxylic acid derivative. Let us first go to the carboxylic acid. So carboxylic acid is prepared initially from the alkanes, and taking an example, we started from alkane. So from hydrocarbon, how can we synthesize carboxylic acid? The very first method says that if there is an alkane which is an alkane in the presence of, so alkanes regularly do not react very oftenly with oxidizing agent. Alkane, as their name suggests, alkane. So alkane are actually also called as paraffins, and paraffins are less reactive. They do not react frequently or very oftenly with all the compounds, and specifically towards oxidizing and reducing agent. So what it will do, under some regulated supply of oxygen and high pressure and in the presence of catalyst, we can bring out the reaction where CH3 which is ethane can be converted back to into ethanoic acid using this manganese diacetate MnCH3CO whole twice. So this is how the reaction works. Simply learn the reaction, simply take an idea how alkanes are converted in this way, and what catalyst do we use, high temperature, high pressure, and that is not an ordinary reaction, occurs only at the drastic condition. Number 2 is from alkene, and we have plenty of reactions using which we till now have prepared all the like carboxylic acid and some other what should I call it, oxidized products. So let's see what oxidized product does it make. We initially have concentrated or alkaline KMnO4. We used to have cold dilute KMnO4, but that is a test of unsaturation called as Bayer's test, where simply vicinal diols are formed as the product. But no, don't go behind that. We'll have to do the, what should I say, oxidized cleavage of double bond in order to produce the aldehydes and ketones. I'll give you some idea that what and how the products are formed. So let us take this example, everyone. Let's say CH3, CH double bond, CH3 is one of the alkene, and now what we are using is hot concentrated KMnO4. This reaction does the cleavage of this double bond and converts all the H into OH, and the product will be CH3, C double bond O, OH plus OH, C double bond O, CH3. So this is the product which we will be getting. So whatever the hydrogen is there will be converted into the OH, and this bond will be broken down into C double bond O. So let us suppose if there was any compound like RR, then maybe this would not have produced the same, because this will give you ketones rather than giving you the aldehyde. Sorry, carboxylic. But yes, if there is one hydrogen over there, then it will definitely be converted into this. So let us say I'm taking one example, or where I'm trying to oxidize this. So initially you will get, this is how you will be getting the product, but this product is unstable. It eliminates out water immediately, readily, and it produces the CO2 gas plus water. The final will be CO2 gas. It's very simple that whatever the hydrogen is there on the doubly bonded carbon, you got to convert it into COH, and the double bond will be cleavaged down into C double bond O. That is what the mechanism has suggested us, and rather apart from that we do not need to learn anything. Just take this thing in your mind that every doubly bonded carbon which has a hydrogen available, that will be converted into OH group, and similarly that double bond will be broken down creating C double bond O group. We have one more thing called as ozonolysis, and the ozonolysis of alkene also follows exactly the similar process what we have learned from the hot concentrated KMnO4. So these two follow exactly the same scenario, same procedure, that whatever the H group is there will be converted into OH, and the rest one will be RR C double bond only. We have a question here, guys. We have a question. So in this question, what we should do so that this can be broken down in such a way, here is double bond. So no doubt this is perfectly what we can see is ozonolysis, and this part is actually oxidative ozonolysis. This is called as the oxidative ozonolysis because this is a hydrogen, and this hydrogen will be converted into OH. That's why this is getting COH. We also know that ketones usually do not undergo oxidation very easily, and that's why ketones will be having their own identity in this reaction. So the correct answer should be B, right? And not just B, it should be initially you use ozonolysis, O3 in CH2Cl2 or whatever the medium you are taking, and then right after that you also need to take what, H2O2 or OH, like oxidative ozonolysis we are doing, or water is also fine. We have next preparation from alkyne. Till now we have covered two three important reaction. Number one was the oxidation of alcohol. Number two was the oxidative cleavage of an alkene, and that was done under two conditions. One was the ozonolysis, another one was the using strong oxidizing agents such as hot alkaline KMnO4. Now we have fourth reaction where we are doing the same reagents, we are utilizing same reagents against an alkyne. So how does an alkyne gets oxidized? So whatever the bond is there, C triple bond O is there. First of all, this bond breaks in such a way that this will create a double bond O and one OH part. Perfectly, I'm right. So see these guys, this is how the reaction works. So let us suppose this is CH triple bond CH. So guys, break this bond under the same oxidizing cleavage, hot alkaline KMnO4, and this breaks in such a way that H will become OH, H will become OH. This already does double bond O and one OH. So we all know that this is pretty unstable. One water molecule will be eliminated out, and then CO2 will be the final product that you will be getting by the oxidative cleavage of this. That's one of the reaction, one of the type of such reaction. Let me present you another such example. So let's say this time we have CH3C triple bond CH. We already know that this component will be converted into the above one only. So rather than that, let us use directly CH3. So this thing under drastic condition, what we have shown there, or like a hot concentrated KMnO4, this will give you the rise of. So now I told you that this C double bond O OH plus C double bond O OH. The triply bonded carbon atom can give you the preparation of carboxylic acid, even if it is connected to two alkyl groups in two-sided. Then we have also ozonolysis of alkyne, and I hope we also have come across ozonolysis in our previous sessions also. Oxidative ozonolysis does what? Let me just remind you. Exactly the similar process will take place. Let us suppose R triple bond is this. This is something which we are doing the ozonolysis, but the ozonolysis should be your oxidative ozonolysis. So what does this oxidative ozonolysis do? Just remove this double bond, this triple bond in such a way that it becomes double bond O, OH, and then also OOH. That's how we make the utilization of ozonolysis. Okay, just take this example. Let's say HC triple bond CH is there, and we are doing the oxidative ozonolysis. So oxidative ozonolysis breaks this bond in such a way that it gives you HC double bond OH. This, under the presence of excess of O3 or like ozonolysis stuff or the oxidizing agent, can also undergo further oxidation, and this further oxidation can give you the rise of CO2 plus H2. Let us try one question. Which carboxylic acid is formed as a result of this reaction? What do you find over here? This is an oxidizing agent, and that too also strong. I told you that whatever the H is there, that will be converted into OH, and one double bond O will be attached with the breakage of this double bond. Another one will be converted into HC double bond O, and then OH. This can remove water inside it, and then can give you the rise of CO2 gas. But along with this, we also have got this acid, which is meth-eth, called as ethanoic acid. B. Hopefully you all are getting me what I'm trying to explain, everybody. So that's how we do. And now let's reach to another important question. We have some more preparations, and that too we are doing it for alkylic. Okay, so we are now supposed to make the benzoic acid. So by how we synthesize the benzoic acid, we'll come to know how benzoic acid are prepared. So guys, we have anything called as alkyl benzene. The necessary condition, try to understand that necessary condition is carbon attached to benzene ring. Carbon attached to benzene ring must have at least one hydrogen. So guys, one hydrogen must be there. So irrespective of how many number of carbon atoms are there, this, let us suppose this is CH3, this is, let us suppose, C2H5, and this is, let us suppose, C3H7. These all undergoing KMnO4 hot alkaline will be giving you the same product called as benzoic acid. Also, even if you are using an isopropyl benzene, it has one hydrogen with it. It is called as cumene. Under the influence of alkaline, KMnO4 and heat, this will give you the formation of a benzoic acid. This is the final product. But what if I am taking a tertiary butyl benzene? But this tertiary butyl benzene has no hydrogen which is directly bonded to the carbon atom bonded with this ring, and that's why in the presence of alkaline KMnO4 and even heat, it says no reaction. So now moving forward, hopefully you all have written this part. Great everyone. We have some questions with us. We got to find out what will be the particular outcome of this reaction. So in oxidizing agent, and let us suppose that we are using the same oxidizing agent which is hot acidified K2Cr2O7, that also does the same work. So this will be doing the same work and will be producing benzene with two COH groups adjacent to each other, and this will have no reaction. As I told you, what is the necessary condition? At least one hydrogen should be there on the carbon atom, or we can call that carbon atom as benzylic carbon atom, the one which is next to the benzene ring. So hopefully this part is absolutely clear to all of you. And now just allow me a sec. Yes guys, so I was just uploading the PPT and the remaining part of this chapter. Hopefully I'm back and I'm pretty much audible and visible to every one of you. Am I? Let me just, yes. So guys, we have another very important reaction with us, everyone. We have to convert this bromobenzene to carboxylic acid, and let's see how can we do it. So the reaction is pretty easy, and this is how the flow works. That initially just convert it into some alkyl benzene, and then you can do whatever you want. I am bringing one magnesium in dry ether. This magnesium in dry ether can convert this compound into phenyl magnesium bromide, which is a good source of an anion R minus, and then we are I need a Cl group there. Okay, so you can simply get is attacked with CH3Cl. So this carbon ion will come, SN2 attack will take place, and then it will give you the formation of toluene. So this toluene, under the influence of acidified K2CR2O7 and heat, or you can call it alkaline K1O4 in heat, and even acidic conditions K1O4 in heat, whatever it is there, or concentrated nitric acid, everything converts back into this compound into benzoic acid, and that's how you are getting your benzoic acid. Clear, guys? Great. Let us solve one question, that which of the following does not give you the benzoic acid? Salt on oxidation with hot alkaline KMnO4. Which of the following does not give you benzoic acid as salt? Great. So alkaline hot KMnO4 can reduce to anything, but not to that alkyl chain which has no remaining hydrogen over benzylic carbon. So that's why this will not upon the reaction with KMnO4, and even no reaction. Clear? Next, second category, like till now we have completed the preparation of carboxylic acid from hydrocarbons, and now we have come to the second category, which is hydrolysis of alkyl halide. So how are we gonna to hydrolyze the alkyl halide? Alkyl halides must contain 3 halogen atom there. I find it, or that can give you COH. So I think I'm correct that 3 halogens on same carbon atom will be hydrolyzed, will be converted into OH groups, which are not stable. One water molecule comes out of this, creating one double bond O, and the final product will be C double bond O OH. And even in the presence of base, it will give you what? CONA. So that's how we can convert anything into carboxylic acid. Even these compound, like this is chloroform, can also be converted into formic acid, and this trichloroethane can be converted into ethanoic acid. Let us solve one question. A halogen compound A on hydrolysis with dilute alkali followed by acidification gives you acetic acid. So guys, we'll go in backward direction. So what is that acetic acid? COH. So this will be formed when you are using 3 equivalents of NaOH, and we are removing 1 equivalent of water also out of some CH3, C, OH, OH and OH. So how would this be formed? When we are using NaOH, we are using, now 3 NaOH are used over here, not over here. Here just water molecule is removing out because this species is unstable. So just connect 3 chlorine. This is how it is going to work. CH3CCl3. D is the correct answer. Clear? Then we have another method of preparation that we can do by from Grignard reagent. Okay, how we'll do? I'll let you know. Wait. Now we'll prepare it from Grignard reagent. Sure. So guys, we already have covered this part that Grignard reagent is a very good resource of R minus, and not just of R minus. Grignard reagent can give you so many good products in yield, like alcohols. Also, we used it in alcohols. Reaction of Grignard reagent with carbonyl compounds gave you alcohols, primary, secondary, tertiary. So here, how are we going to do? Grignard reagent is with us, but we require that carboxy part, and then in order to bring the carboxy part, we have CO2 as a reagent. So take this idea that we initially have any of the Grignard reagent with us, and let us suppose we just have Rx. This Rx under the reaction with magnesium in dry ether. Always remember this equation or this formula, very important reaction. I explained this reaction previously in some of the important chapters, and this has appeared so many times till now, even in hydrocarbon, alkyl halide, aryl halide, and not just over there, alcohol, phenol, ether, aldehyde, ketone, everywhere this reaction was there. Very popular, very versatile reaction that produces RMGX. What is the benefit of RMGX? R contains a negative charge, Mg contains a positive charge. When we get it reacted with CO2, this R minus attacks on the carbon, carbon atom with the high electropositive character, and then electron density shifts into this direction, preparing RC double bond O minus and MgX positive, a compound that under any mineral acid or any acidic condition, H3O plus, dilute H2SO4, dilute HCl, or H3PO4, whatever you want to take, it will convert it into carboxylic acid. So I can see one thing here, that you cannot prepare one acid from here. Using this reaction, there is one acid that you can't prepare, and I must write it, that we cannot synthesize formic acid from here. Formic acid cannot be synthesized. Using this reaction. So we can not prepare formic acid, HCOH, using this reaction. This is the drawback of this reaction. Chalo. Now I'll explain you. Let's see one question. The acid formed when propyl magnesium bromide. So first of all, we know that propyl group is C3H7. This compound contains R minus Mg positive. When we react it with CO2 gas, the attack takes place in such a way that it gives you CH3, CH2, CH2, C double bond O minus, MgBr. Then under hydrolysis, under acidic condition, it gets converted back into CH3, CH2, CH2 and COH. This is called as butanoic acid. So one extra carbon is basically attached in this reaction. The correct answer should be what? C3H7 COH. Only A. B cannot be synthesized. No. Next is by hydrolysis of cyanide. This is one of the very important reaction. And why am I saying that this reaction is highly important? Because it also produces amide meanwhile, and while we going for further hydrolysis of amide, this also yields to the formation of carboxylic acid ultimately. So we can also consider, as per one definition that said that whatever the compound is there that can be hydrolyzed to give you carboxylic acid can be considered as its derivative. So yes, this is also a derivative of cyanide, is also a derivative of carboxylic acid, because it upon hydrolysis produces one reagent or like one equivalent of water. So you add one H2N minus, like you can show this thing like this, C double bond N with one negative sign here and positive sign here. Now you add OH to this group, OH and then H to this group, and they will be forming a compound called as OH double bond NH. What is it? Oxime. And then again do the same. Just remove this bond S and just try to write this bond as COH positive, NH negative, and then again give it the same, OH negative, H positive, that of water, and then two OH are not stable. One water molecule will be removed out and it will give you the formation of RC double bond O NH2. This is called as amide. So amide is formed by acquiring two equivalent, right? This is acquiring two equivalents of water, giving you amide. Then further hydrolysis will give you what? If you further keep on going, then H plus and OH minus, the same thing. OH will be connected here, this bond will be broken down and ammonia gas will be removed out. So this is how this reaction occurs. OH plus ammonia gas will be eliminated out. Now since this is an acid, this is a base, this rather than going directly to ammonia, it sometimes keep on remaining in this acid base mixture NH3 plus Cl minus. Like this is how it usually remains there. What have I made here? Yeah, this was OH, ONH4. Sorry, my bad. O minus NH4 plus. But again, under acidic conditions, we can bring down it to COH. So that is why what we do, we sometimes use some HCl gas meanwhile of the reaction that regularly reacts with NH3 and NH4Cl white fumes get removed every time, and the reaction keeps on going in the forward direction where more and more acidic acid or whatever the carboxylic acid we are trying to make can form. So this has been given with a question here. Try everyone. So try this question and just allow me a moment and I'll be joining you in a just couple of minutes. Try this. I am also giving you one beautiful timer. Start. Okay, do it by your own. I'll come back and join in just a couple of minutes. Yes, so anybody submitted with the answer? So guys, we right now are having some celebration of Christmas there. And they only asked me that, sir, we are cutting the cake, please come and join. So that's why I went for a while, couple of minutes. Now let us focus on this question. PI3. Okay, you all have come across this reaction PX3 and PX5 reacts with an alcohol. The reaction follows SN2 path and it gives you the formation of C2H5I. Now we have synthesized one alkyl iodide. Now KCN does another SN2 reaction and it gives you C2H5CN cyanide, right? Then hydrolysis will yield, ultimate hydrolysis will give you what? COH. This is your propanoic acid. Can you find out the correct answer? Propionic acid or propanoic acid? Both of them are the same. Very nice. Next is, which of the following on oxidation gives an acid containing 2 carbon atom? Acid with 2 carbon atom upon oxidation. Okay, ethanol on 100% oxidation will give you CH3COH. This is true. Ethane amide. So this is ethane amide is CH3 C double bond O NH2 upon fully hydrolysis gives you COOH. Ethane amine CH3 CH2 and ethane nitrile is CH2 like CH3CN. This is ethane nitrile. So this also under oxidation okay, this is correct. This is not we are oxidizing it, we rather than are doing the hydrolysis. We are rather than this we are doing the hydrolysis here. So this can't be considered, or I think the alcohol only is the correct answer. A is the correct answer. Rest all of them will be, they are not oxidized, they are hydrolyzed. And then is in under oxidation it can give you. So I think the correct answer should be only A. Only A is correct answer. No further option. Coming to our next question, we have aldehydic oxidation. Now we are oxidizing the carbonyl compounds, another important reaction of creation or preparation of the carboxylic acid. So we have aldehydes and ketones which can be oxidized using strong oxidizing agent. These all are the strong oxidizing agents and they directly lead you to the formation of carboxylic acid. Rather than stopping the reaction up to aldehyde, they directly convert alcohol into what I can call it, carboxylic acid. And believe me, all the aldehydes, whether it's an oxidizing agent, let it be the weak oxidizing agent or it could be a strong oxidizing agent, it will always lead you to the formation of COH. Now examples are given here. Take the idea. Some of these strong oxidizing agents are these. Some of the weak oxidizing agents are these. Tollens reagent, Fehling solution. And now aldehyde can be directly converted into alcohol, carboxylic acid, but ketones cannot easily go. But ketones, some specific type of ketones which contain methyl keto group, containing what? Methyl keto group. They can be easily oxidized under the reaction called as haloform reaction. So take the example, CH3, C double bond O, CH3. This is a mandatory group present, should be present, and the reaction with halogen and NaOH gives you the formation of haloform. This is called as iodoform. Yellow PPT settles down upon acidic touch or acidic hydrolysis. This gives you the final product as CH3COH. Very easy reaction. We call this reaction as haloform reaction. Which of the following will form propanoic acid on oxidation with KMnO4? So this is propanol, this is propanol. Upon oxidation, let it be weak or strong, it will be converted into COH. So let's say it is a propanone. Propanone is also called as acetone. Under KMnO4, what does it do? It will be broken down from any of the part, giving you C double bond OH, HC double bond OH. That also under the Darcy condition can give you HCO2 plus H2. So remember, these reactions are very much important, and ketones do not give these oxidation reactions very easily, but under hard conditions and specifically when some strong oxidizing agent is given, oxidative cleavage occurs, formation of carboxylic acid may occur, but we have to make sure that this C double bond O goes with the smaller group. We called this rule as Popoff's rule, earlier discussed in the aldehyde ketone chapter, might be known to you. Okay, propionic acid is obtained when glycerol is heated with sulfuric acid. What is the point of this? What we have in glycerol? Glycerol, this is your glycerol. Under sulfuric, concentrated sulfuric acid, what does it make? No idea. One hydrogen is eliminated out. double bond will be formed. No, as such anything will not be formed. Only this can happen here. As a dehydrating agent or as an elimination product, you can form this reaction. Rest it won't change. This is some enol you will get, and then you have CH2OH also along with it. So I don't think that you will be getting any answer from here. Methyl alcohol oxidized with potassium permanganate. What is methyl alcohol? CH3OH, if it is oxidized under strong oxidizing agent, will be directly converted into HCOH just with one carbon atom, and that too is not correct. Propion aldehyde with potassium, I think this is fine. Propion aldehyde is CH3 CH2 CHO. This upon oxidation first and then followed by acidic treatment of dilute H2SO4 will lead you to the formation of CH3 CH2COH, and this is called as propionic acid. Calcium acetate is distilled. What is calcium acetate? CH3 C double bond O minus C double bond O. Calcium carbonate is one product along with CH3COH, but again this is ethanoic acid, not propionic acid. This is ethanoic acid. The correct answer should be what? C only. I have covered all the reactions given here. I would expect you people to follow me, follow all these reactions. Chalo. So C is correct as we discussed. Primary aldehyde gives on like what does it give on oxidation? What is primary aldehyde, by the way? Primary aldehyde? Aldehydes are primary only because this is a terminal group. So let us suppose CH3 COH is CHO is there, and upon oxidation will definitely give you what? Very easy question here. Acetic acid is obtained when? Methyl alcohol oxidized with potassium. What is methyl alcohol? C2H5OH upon oxidation gives CH3COH, ethanoic acid. Acetic acid is correct. This is correct. First is correct. Calcium acetate distilled in presence of calcium formate. So there will be, you will be getting multiple product because one of them is formate, another one is acetate. There is a possibility that we will getting we'll also be getting HCO, like mixtures will be getting mixtures of carboxylic acid. And acid aldehyde is oxidized with potassium. This yeah, this is also give you acetaldehyde. I have no clue now till now. Okay, methyl alcohol was there. This was not ethyl, yeah. C is the correct answer. See, methyl alcohol is CH3OH. So what does it give on oxidation? Just with the one carbon atom, HCOH, formic acid. So this is incorrect actually. The another one is also incorrect because it's giving you mixtures of the acetic acid, like carboxylic acid. C is correct because one acid aldehyde CH3CO H upon oxidation and then followed by acidic treatment gives you C double bond OH. The last one is glycerol on heated with. Are we repeating it or what? We have another method of synthesis. The another method of synthesis is the hydrolysis of acid derivatives. Now derivatives could be acid halide, esters, it could be like all of them can come under this category. Cyanides also, amide also, everything upon hydrolysis gives you these product along with a byproduct. So take it in this way that the carbonyl part, C double bond O part will be attached with OH group of water. The rest part will be attached to H group of remaining. Let's take this example, everyone. This is a general equation R C double bond O, and then we have G here. Break this bond, take water with you, H and then OH, and just add them. Add them in such a way that, let's say this is positive, negative will be added to here. This is positive, the negative will be added to here. So the product will be RC double bond OH plus HG. HG, what is HG? So let us solve some of the reactions. Take example RC double bond O Cl plus water, RC double bond O OS plus HCl, RC double bond O OR plus water, RC double bond O, this ester, this is a reverse reaction of esterification, saponification. This will give you OH plus alcohol ROH, then RC double bond O C double bond O R plus water. Then what should we do? RC double bond O, one of them will be acquiring H and the another will be acquiring OH. So this will be acquiring another. This is how it is formed. And the last one is amide RC double bond O NH2 plus H2O. Plus NH3 gas will be eliminated out. This is how it works. Take an idea, everyone. Please take an idea. Now we have one very important question. There's an ester. Acidic hydrolysis is done. You know the product? C2H5, C double bond O, OH plus the remaining part CH3O, H. So this is the correct answer. C. Very simple. We have another reaction that CH3 C double bond O NH, pH and then working of H2O there does what? So guess what, guys, what will happen here? This will simply work under this I told you once, put an OH over here and H over here. So this will give you what? CH3 C double bond O. OH is one of the product, another will be pH, NH2. Aniline is another product. So since the conditions are acidic, under the acidic condition, aniline will be converted into anilinium ion NH3 plus. Correct answer should be D. Now taking you to next question from here. We have one acid anhydride and find the ratio of A and B. I don't know what is it asking, but let us try this question once. I guess it should be 1:1 only. Because let us suppose, so how does the reaction work? Basically, this is SN2TH reaction, and this will work on least hindered and more positive charge containing carbon. So guys, the product will be C2H5. I will explain its complete mechanism later on. Right now we are just taking the idea how the reaction goes on. These type of reactions are called as SN2TH reaction, bimolecular nucleophilic substitution via tetrahedral intermediate. But we right now just are making C2H5, C double bond O, and then OH plus this complete O minus this group will be eliminated out. So this goes up, this comes down, and this will be eliminated out. So one more compound will be pH C double bond OH. So two acids are formed here. The ratio will be 1:1. The ratio is 1:1. So now we have finished one important part from carboxylic acid, that is their preparation. Now apart from preparation, we'll come to its physical properties, and then we'll come to its chemical reactions. Let's see. Physical property is fun. So guys, lower fatty acids up to carbon number 10, they are colorless liquid, but higher ones are colorless waxy solid. So the important part that we are coming across it is they have higher boiling points even than water and even beyond than alcohols. That is why they exist. Even its lower molecules are existing into liquid state, not into gaseous state. But as we have seen that in terms of alcohols, some of the lighter the alcohols are also liquid. Oh, got it. Hydrocarbons were actually gases. Right. Because they have a typical H bonding, that is why they are liquid. Okay. Now, first three members have sharp, pungent odor, but C4 to C9 are they have an odor of rancid butter. But higher members do not possess any smell. They are smellless. They are odorless. Then we have lower members are highly soluble in water because of their ability to form the H bonding with water molecules, but higher ones, as they contain bigger sized water repellent part, which is the carbon chain or the carbon tail, and that is hydrophobic in nature and doesn't get easily dissolved, and that's why the lower members are easily soluble, higher will not be soluble. And melting and boiling point, if we talk about melting point of carboxylic acid with even number of carbon atom has higher than that one of the odd number, and that has been observed up to first 10 members. So you guys can observe this type of pattern. Like if I'm going graphically, here is the melting point and here is the atomic mass or the molecular mass. So check it out. This is formic acid. This is your acetic acid with 2 carbon atom. That is how it goes. So guys, this is HCOH, this is CH3COH, this is C2H5COH, 3 member, again declined, then increased, then C3H7COH, then C4H9COH, C5H11COH, this is not cool. We had fine. 5 members are here, 6 members are here, 7 members are here, C6H13COH, C7H15COH, like that. That is how their melting point goes on increasing, but the one which are having even number will have a higher melting point, sorry, not boiling, melting point. Now guys, we have another important term here. Carboxylic acid in vapor phase exists as dimer also in aprotic solvent, but in water we have, let us suppose, CH3 COH. If we are in benzene or CCl4, then now take this thing, they are forming a dimer, but where in non-polar or aprotic solvents. But if we take this thing into water, it will be dissociated and it will become aqueous in state, and it will establish an equilibrium. That's how it works. Also, they have a strong extent of H bonding. Sir, where did Akash Tyagi sir go? He's here only. I told you last time that Akash Tyagi sir was not so well and he couldn't come because of his own reasons only, and right now he has some sessions on some other channels also. These days he's busy, so that's why we have come up with Sharath sir. We have the most perfect replacement here, and not replacement, he will come back and join us soon, because you all know that physics is quite vast. Some of the topics will be taken by Sharath sir, some of them will be taken by our Akash Tyagi sir also. Okay, so don't worry, you people keep on study. We'll bring whatever it is needed for you people, so just keep on study, right? That's it. Now because of the extensive H bonding, let me write one more part over here. Because of the extensive H bonding, the general order of boiling point becomes what? General order of boiling point. Like if we compare the molecules of similar masses, then what should be having, which one of them will be having higher boiling point? The number one category comes up for carboxylic acid, because carboxylic acid has so many O and H groups there which can attach to each other via hydrogen bond. Then number two comes your water, has an extensive H bonding. Then we have alcohols. Then we have aldehyde oblique ketones. Then we have ether, and then last comes the hydrocarbons and especially alkanes. This is the general order of boiling point. Boiling point varies in this trend. I hope this is very much clear to all of you. What is the physical state of ethanoic acid? It is liquid, yaar. Didn't we study it? Like the lower members are liquid, higher one are the waxy solid. Pure acetic acid is known as glacial acetic acid, correct? Why? Because it is white at liquid. Because it is white, it is solid as ice, and it forms what? So it is solid as ice below 16.6 degrees Celsius. Okay. As I told you, it also like the extensive H bonding is even more in carboxylic acid than comparing to water, and that is why even upon 16.6 degrees Celsius it freezes. So that is why pure acetic acid, which is also called as glacial acetic acid, is kept like above this 16 only. Next, acetic acid does exist in dimer because of the presence of hydrogen bonding. Then which of the following has the highest boiling point? The boiling point highest will be shown by the biggest molecule. Okay, they are all are different. See, this is ether. This is ether. This is alcohol. and you can compare that they all are having similar like mass. This is your alkane and this is your carboxylic acid. So the correct order should be C, B, A, D. This is the order of boiling point. Your answer is C. Got it, everyone? So as I have told you that we have this very important All India mock test series going on for all the JEE aspirants of 2025. You can give your examination on our platform. It's absolutely free. Go and enroll right now. The link is given in the chat box itself. You can find out your enrollment link over there. Just go enroll yourself and make sure, guys, make sure that you people are now working on this very real exam simulation process where latest curriculum will be followed, and most importantly, all the educators are involved in preparation of these questions, which are highly important. Many of these questions will be not just virtually, but in fact really gonna to appear in your coming exam also. The similar concepts, similar questions, and not just that, it also gives you the rank predictor. So that will help you to know that where do I exist, what should I work upon, and how can I come up at the top if I'm not right now at the top. So this is what you can do by our All India mock test. The link is given right in the chat box. So now we have chemical properties. So guys, starting with chemical properties, we have number one property called as acidic nature of carboxylic acid. We all know that a carboxylic acid can lose their H positive and can form their acetate ion that can basically, or carboxylate ion that can which is the resonance stabilized and gives you this kind of resonating structures. These two are actually the resonating structures, RS, and this one is called as the resonance hybrid, RH. So just take a note that carboxylic acids are weaker than all the mineral acids, and they are also stronger than alcohol and simple phenol. So this is somewhere we can take this idea. I have already completed one of the I remember second chapter, second day lecture only. Second day lecture, I remember second day or third day, I guess third day, second or third day only, maybe second day, where I taught you the application part of all electronic effects, and there only we understood the concept of acidic and basic strength of organic compound. So guys, please revise it, because that is the one chapter in which you can cover all your basic doubts related to all type of acids that may exist in organic chemistry. And I gave you the idea how can you determine the acidic strength and compare the acidic strength between the two of the acids. Although I'll give you some of the idea over here also, but my suggestion is that if you want to do the mastery in the topic or mastery in the concept, please visit there. It's a separate playlist made of organic chemistry in class 12 chemistry, and in class 11 chemistry was also there in GOC. Second lecture I have taught it. Now we'll come to that acidic strength is directly proportional to the stability of conjugate base. So let us suppose that, what does it mean? What does it mean? It means that, let us suppose we have C6H pi, COOH, we have CH2I, COH, we have CH, so guys, try to understand what I'm explaining here. these are some set of acids. Okay, these are the acids, and not just simple acid, they are all carboxylic acids, different type of carboxylic acid. Right after losing their H positive, they will give you a carboxylate ion, that will be C6H5, CO negative. This is CH2I, CO negative, CH2Br, CO negative, CH2, CO negative, CH2CN. Now you please examine this order and let us just know which one is more stable. So guys, we can see that this is the order of stability of conjugate ion, and we all know that higher is the stability of the conjugate ion, the reaction will try to go into that direction by losing more and more H positive. So that's why the acidic strength also increases in this way. This is the order of, this will become the order of acidic strength called as Ka. Dissociation constant of weak acid, Ka. All set, all clear? Similarly, we have some more examples which can easily be done now. I told you that moving from left to right, the acidic strength Ka decreases, negative logarithm of Ka increases. Now, similarly, if we talk about these all, what do you think? What do you think that what should be the acidic strength? This will be like CO minus COH. So, are you observing this part that for one of the CO, the another one is working as minus I, but the distance has increased here. It is lesser minus I. This had more minus I, and then coming to the third one, we have CO minus this is an electron withdrawing group, but lesser minus I. The lesser minus I is there, that's why the acidic strength should be like that. Next comes the acidic strength of aromatic state. If we talk about aromaticity. So guys, aromatics are no doubt more acidic than the aromatic one lose their H positive and they form carboxylate ion like this. This is called as benzoate ion, and under this, what do I see? This negative charge is stabilized by the minus I effect of the ring, because you all know this causes what? Minus I effect. But if you talk about ROH, not ROH, RCOH, this will also lose H positive, giving you RCO minus, and this might be resonance stabilized and exactly the same one over here, but this group R does positive I, increasing electron density. So we all know that which one will be more stable. If we compare the carboxylate ion, this is more stable. If this is the order of stability, the reverse, this, no, not reverse, exactly this will become the order of acidic strength Ka. Remember, गाएगा ये ज़मा, गाएगी ये ज़मीन. So guys, generally benzoic acid is more acidic than aliphatic carboxylic acid, but only methanoic acid is more acidic than benzoic acid. So overall what you can see is the overall order becomes PHCOH is even lesser than HCOH, but rest of the RCOH will be weaker than benzoic acid, the order of Ka. Remember this point, it's a very important point. Now explaining very important part of this acidic strength. तुम कभी कह रही गाएगा ये ज़मां गाएगी ये ज़मीं. दोस्तों, next comes is the ortho effect. Now let me explain you what is ortho effect. So I have already explained this part in the acidic strength, but I am just again explaining it. Ortho effect. We also call the ortho effect as SIR effect, SIR effect. This says, it's very simply, it says that if any of the benzoic acid is connected to electron withdrawing group, let it be ortho, meta, para, this will be a better acid. This will be a stronger acid than normal benzoic acid. We all know this is the order of acidic strength Ka. Similarly guys, if benzoic acid is connected with any electron releasing group will increase the electron density of the conjugate anion, making it more unstable, but this should be at meta and para only. Then again, normal benzoic acid will be more acidic than the one which is substituted with releasing group. But last and most importantly, you will find a benzoic acid which has any group G, which could be electron releasing group or electron withdrawing group, doesn't matter. It will always be more acidic than a regular benzoic acid, and this is the fact I was talking you about. This is because of due to ortho effect. So that is what we have to understand now. So what is this ortho effect? We'll understand it now. So what usually happens whenever any benzoic acid is given to us, we are just examining that how does this acidic strength work. So guys, this electron density wants to join like this, but and this comes wanna come like this. So one of the resonating structure of this looks like this. This is not a resonance sign. Pre-resonation. No, kidding, man. So anyways, this works like this. O negative, OH positive. So what you can observe is that higher is the positive charge arising on oxygen of OH, more easily hydrogen departs as H plus. More easily it departs as H plus. But what is happening here? Now you see, this electron density is not letting this positive charge, this is interfering. So what we can say, that resonance of benzene diminishes the positive charge on oxygen, making carboxylic acid less acidic. Now please read it out what I'm saying. Please read out that this is not working as an acid until or unless, like, no, this is working as an acid but not a strong acid it is working as, and this is all because of the COH group, this benzene ring which provides the electron density makes it less acidic. But guys, whenever we put any group G, these two interfere each other sterically. So due to the steric hindrance, you can say anything can go out of the plane. Let it be the planarity of ring, or we can say the group. The group, we should say that group goes out of the plane of the benzene ring. Maybe the ring might be going or the group might go. It's obvious that both of them are not in the same plane now to carry on the resonance. So due to the steric hindrance, the COH group goes out of the plane of benzene ring and resonance stops. And since the resonance stops, it becomes more acidic. Getting me? That is what the ortho effect is all about. So now which of them is more acidic in nature? So guys, you all know that HCOH will be more acidic than acetate ion, acetic acid. Then this is the order of Ka. Then we have which is more acidic among formic and benzoic. As I told you earlier that formic acid is the only acid which is even stronger than benzoic acid. I don't have the exact data with me, but I assure you that rest other carboxylic acids are weaker acid. But this is up to when you are not having any external help. The moment you take an external help, for an example, if I put any group Cl over here, even with the presence of Cl, this become more acidic. Not Cl, let us take NO2. Next is another reactions which involve the proton, or we can say the acidic part of an acid, carboxylic acid. The very one reaction is whenever an acid reacts with a metal, it produces hydrogen gas. Take any example. Let us suppose this is the metal and CH3COH acetic acid reacts with sodium, producing CH3COO minus Na plus, a salt. Along with hydrogen gas. And similarly, with alkalis, it gives you salt plus water. This is called as potassium acetate, and plus water is formed. So salt plus water, acid plus base gives you salt and water. Got it, guys? Next, one question is here. Select the strongest acid in each of the following set. You need to select the strongest acid. So guys, as I told you, what works here? Ortho effect. Let us just make all of them. So sir, over here we have one just COH and COH connected to NO2 at ortho. A. What is the need of writing all of them? Just simply say that over here ortho and para directing groups are nitrogen NO2 group creates a positive charge on ortho and para, and this also lies on ortho. It will be affected by its resonance. So we can say minus M effect works over here more than the minus I effect, because mesomeric is always dominant over inductive. But in presence of NO2 at ortho, only ortho effect dominates. Or I must write it SIR, steric inhibition in resonance. The SIR effect is also called as the ortho effect that we just studied. Over here there is no resonance working or mesomeric working, only we can say that minus I effect is here, only minus I. Here again minus M might be working more than minus I, and here we have nothing. So the correct order should be, the correct order of Ka will be what? One with the ortho effect will be the best, A, then we have C, then we have B, and then last is A, or not A, or D. D. This is the order of acidic strength. Now you check out, your correct answer will be A. And please guys, try solving question with me, yaar. And if you don't know anything, if you face any doubt, do let me know. I'll help you. Definitely help you. Now take this another such example. So okay, do remind one more thing, guys. I want to remind you one more thing, that there are some very small sized groups which are present, and they are hydroxide, NH2, cyanide. They have no ortho effect because they are very small in size. They cannot displace the COH group into the out of the plane of the benzene ring. So no ortho effect is seen here. But in case of these groups, NO2, R, alkyl, halogen, COR, COH, everything will be working as ortho effect. Okay, now we have another question, similar question. Here we have nothing with us. Here we see that OH group does what? It's a positive M effect more than minus I. It is doing a simply minus I effect because this is so far. This is not at ortho and para to the respective group. Here also positive M will be dominant over minus ka I. But beyond these two, the SIR effect will be dominant. So SIR will make this compound most acidic. So this will become what? The order of Ka becomes what? D. Then where you can find the negative is C. Then it comes with A, and the most worst will become your B because of the positive M effect of OH group at para position. So D is the correct answer. So that's it, guys. That's it up to the acidic strength and all. This is something that we have already covered, so won't take too much of your time, and I will directly come to another chemical reaction of carboxylic acid. What are these reactions? These reactions are called as bimolecular nucleophilic substitution reaction with tetrahedral intermediate. Tetrahedral intermediate. Through tetrahedral intermediate, we will reach out to some reactions. Let's try it. So nucleophilic acyl substitution reaction takes place on addition elimination mechanism. It's a bimolecular nucleophilic substitution reaction with tetrahedral intermediate, where leaving group and nucleophile is eliminated depends upon the relative basicity, and the weaker base is preferentially eliminated out because of the weaker is basic, weaker base is better leaving group. So this is how the reaction works. The mechanism is pretty simple, everyone. The mechanism says that there is RC double bond O leaving group, and the attacking part is your nucleophile. Nucleophile first attacks here, then intermediate will be a O negative, Nu negative, Lg. This is something with a negative charge here. This is something with a negative charge here. So at last leaving group departs, and then it acquires the original carbonyl group plus another nucleophile over here. So this is called as SN2TH reaction. And why are we calling TH tetrahedral? Because this is that tetrahedral intermediate. This is the tetrahedral intermediate. Then comes reactivity order of acid derivative toward nucleophilic substitution reaction. Like if we talk about all of them, so this reactivity order is directly proportional to the stability of leaving group. Stability of leaving group, and the stability of leaving group is, guys, generally halides are most stable, followed by this followed by OR minus and followed by NH2 minus. So this is the order of what? Stability. And that's why the order becomes order of SN2TH reaction among all the derivatives will become that halides, acid halides have the highest, followed by carboxylic acid anhydride, followed by esters, and then followed by amides. Acid anhydride, ester, amide. This is the order of reactivity. So note this thing down. This is very important part, will be multiple times used in the ongoing chapter. This part will be used multiple times. Let's solve one question. Rate of reaction is faster when R. R is what actually? Methyl, isopropyl. So guys, we have this intermediate with us. So R, O negative, Nu negative, leaving group is a negatively charged group, and from sp2 hybridization carbon has reached to as you can see from sp2 hybridization the carbon has now reached to sp3. So much of hindrance. So everything is now dependent upon R. So R simply says that bulkier is the alkyl group. Bulkier is the alkyl group. Lesser is the rate of SN2 reaction. The correct answer should be the less bulkier. Hydrogen should be the correct answer. Hydrogen is correct, see. So now we have chemical properties of carboxylic acid, and we will now, because of the OH group, will do it, and we will do some acyl chloride formation, esterification, amide formation, and anhydride formation. This is what we'll understand now. So now a few of the properties of the acid halide have been already covered. Few more will be known, and that will cover up this entire topic then. First of all, we must know, we are now reading how acyl chloride formation takes place from its acid. So there could be some several reactions. The mechanism itself follows SN2TH. Nucleophile is Cl. Attacking nucleophile is Cl. Leaving group is OH. And this is in the analogous to, like we already covered this part. You will remember ROH with phosphorus and halogen used to produce RCl. You remember these reactions, no? ROH with PCl5 used to produce RCl, POCl3, HCl. Remember? With PCl3, 3 equivalents were used, produces 3RCl plus H3PO3. So guys, you must remember, in the analogous to those reactions only, remember we are doing the reaction for RC double bond OH, exactly like SN2TH we are doing. Instead of SN2 we are doing SN2TH. So Cl is coming, removing the OH part and then acquiring the position. These all are acid halides. Again, the best method will be with SO2Cl, SOCl2, because the leaving group are both gaseous, which are eliminated out of the mixture, and that's why we can get the pure product with high yield. Please read it out. Since these reactions have been already covered, I am not revising this similar part here, but I guess this part is absolutely been already taught to you. चलिए, next is Fischer's esterification, that is the preparation of ester. So guys, I'll give you a shortcut, and I have already explained this reaction to you. This is a very easy reaction, by the way. So how does this reaction work? Okay, so guys, I was teaching you that how this reaction works. So you will be given up with two things. One is RC double bond OH, and the another one that reacts with it is an alcohol, R-OH. It seems like that RC double bond OH is more acidic, acid are more acidic. This carboxylic acid might be more acidic, and it must give you the H plus, but it doesn't happen like this. Focus on the mechanism. The mechanism says that this OH group is eliminated out. So what you will do, this H of alcohol, let us suppose this is O18 here. So this H of alcohol and this D of this will eliminate out. This reaction goes up like this, and then in acidic medium, this is the compound form. O18R dash will be added here, and H2O will be eliminated out. This is the esterification, and this is the shortcut I'm telling you. This is what you can go for any reaction, and you can find your final answer. Now I'll lead you to the mechanism part. How does the mechanism work? So let it be any kind of acid is there, whether it is aliphatic or aromatic, all of them shows a similar reaction. But we will learn that how is this OH group departing. So this reaction occurs only in acidic condition. The reaction occurs only in the acidic condition. So what happens in acidic condition? I cannot disturb this reaction. It's already looking very beautiful and very well explained. I can't disturb this mechanism. So just simply see, initially H plus was there. This oxygen will attack because it is more free comparing to this one. This is how the OH has been formed. This attacks on this carbon, carbon as nucleophile. This is your nucleophile actually. With the addition of nucleophile, that electron density shifts to oxygen, hydrogen departs and gets connected to the this ROH. One was OH, one another is OH, and here is the ROH with a positive sign. With this positive charge is now eliminated out by this. Now what happens in the next step? This hydrogen, it departs and intermolecular proton transfer takes place, forming water which eliminates out, forming RCOR. So wherever this OH group is departing, now see, in the form of ROH, this OH group of RCOR is departed. This is actually departing here. These two are the same. Are you getting? Same. And finally you will be getting a ester as a product. So hopefully champions, you are getting what I'm trying to explain. Like how the reaction works and how you need to decide what has to go. So more or less simply just follow what I told you, and that will be more beneficial. Whenever you are giving with R, C double bond OH, let's say this is like ROD, deuterium, and this is like 18. So the reaction takes place in such a way that it will be connected to ROR dash, and this will become DOH. 18 also is here. Always remember this part. D from here, OH from here. Next is one question, exactly the similar question what we have just studied. So there is one carboxylic acid with one oxygen 16 here, one oxygen 18. We all know that this part goes here and attack, goes up, comes down, and this whole departs OH 16 wala part. Or just make it simple, that H from here, OH from here goes, attach it directly. What you will be getting? C double bond OR, this is R and this is O18, plus water will be H2O with 16. Check it out, the correct answer A. So Akash Tyagi sir will come back and join us soon. He wasn't well meanwhile, what I came across. Hopefully he'll be getting recovered well, and then he'll start taking lectures for us also very soon. A is the correct answer. Next is amide formation. So what we are doing is we are preparing every single derivative out of carboxylic acid only. Again, same SN to TH process, nucleophile will be NH2, leaving group is OH minus, carboxylic acid reacts with ammonia to give the ammonium salt first of all, and then on heating it eliminates out water forming amide. This is how it look like. So on heating this eliminates out. No requirement of any further mechanism, it's very easy. That one first of all, just whatever the how many number of COH groups are there, depending upon that you will make the ammonium salts. All the ammonium salts of carboxylic acid will on upon heating lose out H2O, 1H from NH4, oxygen from the CO group, C double bond NH2 will be formed as a amide product to you. And if you strongly heat it, it also eliminates out ammonia and it forms phthalimide. This was phthalimide, phthalimide. Check it out, thalamide versus thalamide. So that's it. Now let me take you to other questions. We have one question here that in the reaction, this is the reaction, what should be the reagent? We all know one ammonia is given and then it is done. Guys, this is called as phthalic acid. This is called as phthalic acid. And if we provide it ammonia, it will make C double bond O NH2 and C double bond O NH2, and right after strong heating it eliminates out one ammonia and gives you the final product of thalamide, which is this NH. Check out the correct acid, phthalic acid. Another reaction is anhydride formation. So anhydride formation is not first, it is the fourth actually, because till now esters are made, acid halides are made, amides are made. Now the left one is acid anhydride. So what we have to do in order to prepare the acid anhydride, this reaction is sent to TH, same, nucleophile will be CO minus and then relieving group will be OH, and the reaction takes place under strong dehydrating agent. So what we use is, we simply use a dehydrating agent. Now this dehydrating agent could be either concentrated H2SO4, we require a dehydrating agent so that the reaction goes forward easily. These could be concentrated sulfuric acid, concentrated phosphoric acid, P2O5 or P4O10. So this is what we need in these reactions. So two acids are combined to produce one acid anhydride like this. What product is formed when acid anhydride is treated with P2O5? No, acetic acid. So C acetic acid is what? CH3 C double bond O OH, and the another one will be so guys, do one thing I told you, remove one water molecule out of it and just heat them. This is what you get as the final product. What is it? Acetic anhydride. This is your acetic anhydride. Next is reduction to alcohol. Some different reactions now we will be dealing about, other reactions of carboxylic acids. The first one was the acidic reaction where H plus was utilized. The very next one was your use of OH group, hydroxyl part. And now third one is some other reactions which will include all the remaining equations, all the remaining reactions. The number one is called as reduction to alcohol. So using any strong reducing agents such as LiLH4, ether, or like B2H6 or water, or this can lead you to the formation of RC double bond OH2 alcohol. But NaBH4 does not reduce carboxylic acid group. Make a point. Then we have another important reaction called as Hell-Volhard-Zielinski reaction. Hell-Volhard-Zielinski reaction. So guys, this is a very important reaction because usually been asked previously in some of the examination. How we should remember, how should we learn this reaction? I'll give you the clue. So guys, this reaction only works in those cases where one at least alpha hydrogen should be there. This is the alpha carbon, alpha hydrogen must be there. And this reaction happens in the case of X2 and red phosphorus followed by water. This reaction eliminates out one hydrogen and forms X over there, and the remaining one will be HX. The eliminated will be HX. Got it? Alpha halogenated product will be gained. Then guys, here we have the mechanism. So you people just go through the mechanism once. We will be connecting back. So we have one important conversion here. How this reaction works, I'll explain it to you. So initially we have phosphorus plus bromine, which can give you either PBr3 or PBr5, that easily converts ROOH COH into COCl. So this is how CO. Now what has happened here? Yeah, C double bond O. C double bond O Br. Okay, just ignore this part. It undergoes enolization. Enolization will give you the hydrogen. OH group will be formed, and this is how it will look like. I don't know why. This will be connected here. Then enolization will occur. This is actually belongs to here. Okay, this is just remove this part. Not required. Anyways, then this enol formed also undergoes further bromination. How? We all know. This alkene attacks here. One bromine will eliminate out. One more bromine will be attached here. So this is an intermediate where we can see two bromine atoms are attached here. One is here, another here is. The final state is the intermediate A now reacts with another molecule of carboxylic acid, and interchange of Br and OH takes place from the halogenated acid. So what is happening exactly over here is this halogen exchange is happening here. This will be replaced by Br, and finally you will get alpha bromo product with acid bromide. Alpha bromo product is what your main product is. But I would like to suggest you are not supposed to learn down this mechanism. My personal suggestion is, because there is no requirement, there is no question that comes on the mechanism part. The only question that may arrive is direct equation. There is a question, and that may involve you to ask some of these questions. So please maintain that, remember the equation reaction properly, that is more important. Learn it like the way I'm teaching you, but no need to learn down the entire mechanism, not required at all, and especially this HVZ. We have one question here, that which of the following will not undergo HVZ. So this requires an alpha hydrogen is there. This requires an alpha is there. 2,2-dimethyl propionic acid is, so 2,2-dimethyl is here. So meth hath prop. See, this is your alpha, and there is no alpha hydrogen, no reaction. That's it. C is the correct answer. 2-methyl propionic acid, it may give. Already we have got the answer, but we are checking. 2-methyl propionic acid. But this, it has alpha hydrogen, so it will give you. We have next equation, next reaction of carboxylic acid is a dry distillation of calcium salts of fatty acid. Dry distillation of calcium salts of fatty acid, and we already have covered this reaction earlier. Simply do one thing, everybody. We have any salt of any carboxylic acid like this, R C double bond O minus, and then it is connected to Ca2 plus, and then with another one more molecule, let's say. In this reaction, if you heat this system, one of the calcium carbonates depart like this. So what eliminates out? Negative of calcium carbonate, and the product will be RC double bond O. R. Ketone basically will be the product. And CaCO3 is eliminated out. So this is the product that we receive from the dry distillation of calcium salts of carboxylic acids. So this is a free radical mechanism, everybody. So anyone can make whatever they want, and radicals of these are created. So the respective product will be CH3 C double bond O, CH3 C double bond O H, and HC double bond O H. These are the actually products. There's a mixture of product will be received as a product. Next question. Consider the following reaction where CH3COH plus calcium hydroxide and heat. What does it give you? A ketone, I guess. As I told you till now, it will first form a salt of CH3CO minus whole twice Ca2 plus, and that upon heating will be giving you what? A ketone along with calcium carbonate. Fourth reaction comes up as soda-lime decarboxylation. Soda-lime decarboxylation. This is something that we have already covered under 11 standards organic chemistry. In hydrocarbons, we have studied this reaction. We require soda and lime in 3:1. Soda-lime is in 3:1. What is the use of every single species? Let's check. First of all, we have the sodium salt of NaOH that upon heating with NaOH and CO gets converted into RH plus Na2CO3. So what is the importance of this NaOH? What does CaO do? Everything we'll study one by one. So this is the mechanism of soda-lime decarboxylation, I guess. Yes, this is the mechanism. Check it out. So initially it will get converted to CO minus and Na plus. O minus rearranges itself, leaving the CO2 gas behind, and a stable R minus is produced, which immediately attacks on the water molecule, leaving behind OH minus, and RH is the alkane formed. That is how the reaction works. Next is decarboxylation of beta keto acid. This is one more another important reaction. Beta keto acids on simple heating, they gets converted into ketone, leaving behind the carbon dioxide gas, which is called as decarboxylation. So check it out. This is carbon, this is your alpha, and this is your beta. So beta itself is a keto. Beta keto acid is beta, carbon itself is a part of keto group. Then the reaction occurs. Look at this example. We have COH group, and this one is alpha, this one is beta. This beta will remain same. This eliminates out as CO2 gas on heating, gives you acetone. So there we have the mechanism. Please read out to the mechanism once. I'll come back and join you soon. Please read out this mechanism once. We are taking a small break from here, everyone. And you please carry out this reaction. Read it out. Hi guys. Hi, yeah, so I'm back. And where were we, by the way? Okay, so guys, we till now have finished one very important part of this chapter, that was preparation of carboxylic acid. Chemical reaction of carboxylic acid were going on, and mainly reactions of carboxylic acid has been finished, like some of the reactions such as the acidic behavior. Another reaction was where removal of OH group participated. This reaction is decarboxylation reactions, and decarboxylation reaction may happen in various cases. For example, we learned till here one of the reaction name was soda lime decarboxylation, that used to give alkanes as the product. The another decarboxylation reaction was Kolb's electrolysis. We have studied it in our previous some classes, hydrocarbons chapter. Then we have this another decarboxylation called as beta keto acid. It's a very simple mechanism. What actually happens, it forms a cyclic transitional state in which some of the bonds are rearranging themselves to give you the final ketone as the product, or aldehydic product, where you will be removing CO2 gas. So this is called as decarboxylation. So we don't need to worry about the mechanism part, specifically focus on what reagent has been given, what has to be applied, what will be the product. It's simply that beta keto acid and ester, both of them are unstable, so they will break down, releasing CO2 gas. Check it out, the mechanism. So now check out the mechanism part. The mechanism is pretty easy, that beta keto acids undergo decarboxylation through cyclic transition state. It's a one-step process. A simple heating take place, and the C double bond O group, that is the keto part, the oxygen attacks on hydrogen, CO2 group departs, and formation of ketone takes place like this. So first it forms an enol which tautomerizes to give you keto. Exactly right. Next is one question. The decarboxylation reaction of which of the following gives you 1122 tetrabromoethane? No, yeah, man, what is it? Decarboxylation of which will yield 1122 tetrabromoethane? Like something that might be having, like possessing these groups specifically. Maybe we haven't covered this part till now, yeah. I don't see any such. Wait a minute. Okay. First of all, we have to understand this reaction. Then we'll come there and then we'll understand it. It's a simple decarboxylation reaction. A reaction in which decarboxylation, that means removal of CO2 gas occurs, is called as decarboxylation. And when two carboxylic acid groups are attached to the same carbon atom, then this reaction occurs, and decarboxylation takes place simply on heating. So this is exactly like the keto thing. If we observe it, everyone, till now we understand that beta keto acids are unstable. Beta keto acids were unstable. Easily on heating they used to eliminate out the CO2 gas and relieving the ketone behind. So where this kind of compound we were seeing till now, this kind of compound we were seeing simply on heating, giving CH3, CO2 gas is eliminated out like that. You remember? Now the another category is, this is beta keto. This is also comes under the same category. So like if you are having CH3, like let's say COH and CH2 and C double bond OH, isn't it the same thing, guys? So this is your, earlier we were checking it out, like this was alpha to which COH group was attached. This is beta. Similarly, this is COH group, this is alpha, and this becomes your beta keto. Again, beta keto is there, just simply do the heating and then it will eliminate out CO2 gas and leaving behind this acid with you, which is OH C double bond O CH3 plus the gas removed is CO2. As simple as that. As simple as that. But these reactions are very much important, everyone. Then we also have one more decarboxylation, which is simple decarboxylation. Decarboxylation reaction mechanism is given here, everyone, and I guess it follows the same mechanism, the same rearrangement of the molecule, where CO2 gas is eliminated out, giving an enol content, and this enol on tautomerization gives you the carboxylic acid. So decarboxylation reaction, one of the example is given to us, and I told you the simplest way to deal with it. We have one COH group over here. This is alpha, this is beta. This beta, this will be eliminated out in the form of oxygen, like CO2, in the form of CO2. No. What I'm doing is, this will retain there. This will be eliminated out. So minus CO2. The remaining will be written down as it is, OH C double bond O, and then it becomes CH 2CH3. So method propanoic acid is formed. That's how we do the decarboxylation of one which is containing beta keto. Now beta keto can be present in the case of only ketonic group, or sometimes it can be double carboxylic acid also presented or connected with the same carbon atom. Then it will again become the beta keto kind of arrangement. So now, where is that? One more decarboxylation was there. I'm not finding it. I don't know where is it exactly. Beta keto was there. Decarboxylation. Beta keto was there. Soda lime was there. This was there. This has been done. So maybe. Beta keto is done here. Anyways, we'll move forward and we'll find out wherever it comes. So this decarboxylation has also taken place. Now the next decarboxylation reaction is something where Hunsdiker decarboxylation is called Hunsdiker. So guys, in Hunsdiker reaction, what we have is silver salt of the monocarboxylic acid when heated with halogen, and in non-polar medium or partially polar medium undergoes a free radical reaction, giving you alkyl halide as a product, and AgBr is settled down. And this is what happening is, and CO2 gas is also eliminated out. If you check out the mechanism, this is what I have explained you already. So this reaction, this, I don't know what's happening, but I'll explain this part to you. It actually contains two things here. So one thing is RC double bond O negative, and we have Ag positive. Getting me? So guys, there are two things that will happen at the rate anode. Anode always happens with the oxidation. Anode always takes like oxidation takes place at anode every time. So we can make this reaction as RC double bond O negative 2 equivalent will produce 2RC double bond O radical plus 2 electrons are eliminated out. This reaction is called as, undoubtedly this reaction is oxidation. Then we have reduction. There are no reduction at the rate cathode. So cathode allows the substance to undergo Reduction. So how come reduction is going to take place? We have silver also with us, no? But before that, I have one thing remaining. Let me cover that. That this radical undergoes some movement like this, where R radical is formed, leaving behind CO2. So this is your R radical, and we have CO2 gas. And there are like one were there, so 2R and 2 CO2 are eliminated. So R radical plus R radical gives you what? This is RR, which is an alkane. Then we have cathode. Cathode, no doubt redox reaction happens with oxidation reduction simultaneously. So simply silver radical accepts 2 electron and settles down at Ag. So silver salt of fatty acid on heating with halogen gives what? Alkyl halide as a product. Oh yaar, why did we make RR there, yaar? Hans-Diker reaction was going on and I mistakenly reached to, my bad, yaar. This is Kolb's electrolysis. I reached mistakenly, everyone. My bad, yaar. Lost somewhere. What reaction is going on? This is your Hans-Diker reaction. Yaar, not required with this much what I did. So the simple reaction says that this is how it look like. And the 2 radicals are there. The similar rearrangement take place. R radical is formed. We had Br radical. Br is the product which we are getting. And apart from that, AgBr will be settled down. CO2 gas will be eliminated out. So alkyl halide is the correct answer. Next is Kolb's electrolysis is the one which we are right now talking about. So in Kolb's this happens like this, that at the rate anode you will get oxidation. So 2 anions will come, CH3 CO negative, losing 2 electrons to give you CH3 CO radical, and 2 electrons are lost. This is called as oxidation. Now these CH3 C double bond O radical jumps like this. These 2 electrons come like this, and it leaves behind 2 CO2 and 1 CH3 radical with 2 CO2 gases eliminating out. And also this CH3 radical combines with another CH3 radical producing C2H6. So the only difference between soda lime and this reaction is that soda lime produces RH as the product. RH is one of the alkane as a product. This also produces alkane, but the product will be RR. And this reaction is not suitable in synthesis of the like tertiary or 3-degree carbon is there in alkane. That is not possible under this reaction because of the bulky nature. It actually undergoes the preparation of esters is taking place. This directly combines to give you the ester because the bulky radicals are not stable somewhere. Similarly, that is something happening at anode. You can reach out to cathode. At the rate cathode reduction takes place. The reduction reaction is accepting electrons. So what we have is I guess water will be oxidized, water will be reduced here. The water will acquire the 2 electrons and then will form H2 plus OH minus 2OH minus this will be 2H2O and 2H2 will be removed like this and 2OH minus will be removed like this, and this is now balanced. So that is what happens, reduction. And which gas is eliminated out? Hydrogen gas is eliminated out. You could have simply taken H radical also, including H radical electron getting and then forming this. That part all can also be done. Not radical, H positive we could have taken. Columns electrolysis of sodium salt of butanoic acid gives you what? Now these reactions are very easy because we have already covered this part even under hydrocarbon chapter. So Kolb's electrolysis of sodium salt of butanoic acid. First of all, we must know what is the sodium salt of butanoic acid. So butanoic acid is CH3 CH2 CH2 CO minus Na plus, and electrolysis is done. So guys, we all know that this will produce a, after removal of CO2 gas, it gives you a radical CH3 CH2 radical that will combine with another such radical, and RR is formed there. That is the beauty of this reaction. So the correct answer should be method prop butane, method prop but pent hexane will be the product, N-hexane. So A is the correct answer. Let us check. N is the correct answer. A is correct. The next reaction is called as Schmidt reaction. The Schmidt reaction is actually very important reaction, and the ultimate product of Schmidt reaction will come up as amine. What I should say that this reaction gives you one less carbon containing amine, and there are some similar reactions. Schmidt reaction is one of them. Hoffman bromamide reaction or Hoffman degradation reaction is also one of the same example, and probably we'll deal with the same example in here also, but just giving you the idea that how this reaction works. So okay, let's see. So we have hydrozoic acid, we call it hydrozoic acid N3H, that combines with RCOH producing RNH2 as amine, CO2 and N2, and the reaction mechanism is right over here. Everyone, you can take an idea, but do not learn down in this part, not so important for all of us who are preparing for mains, and even in advance this mechanism has not been asked, but yes, there are some certain points that I will highlight out of this mechanism. So initially what's happening, we are adding one hydrogen because we are carrying out this reaction in acidic medium hydrozoic acid. This acquires this hydrogen, let's say, producing a compound like this, which was attacked by the hydrozoic acid or alkyl group, and it gives you Rn, like this kind of compound is come CO2, and after removal of this so guys, what's happening here, let us explore. So initially RC double bond O and NH is something that has been formed out of this reaction. Now this reaction wants to eliminate out the N2 gas. That's why the electron density from RC bond is now coming towards nitrogen, where nitrogen leaves in the form of N2 gas, and the so formed compound is your RNH this, and after removal the H also. Anyways, so actually it doesn't work like this. Like somewhere we get the isocyanate ion, and right after this only. So whenever we are getting R N double bond C, double bond O, and we also had one hydrogen attached here, a positive charge. In the next step, hydrogen departs and forming an important compound. This is alkyl isocyanate. This alkyl N-alkyl isocyanate is a very important compound and very much useful in the preparation of amines, one lesser carbon containing amines. Okay, this reaction is Hofmann bromamide. All of these reactions occur in the similar way. See, but actually that reaction was carried out in what should I say, basic medium. Schmidt reaction carries out in acidic medium. So this is where hydrogen won't eliminate out, because there is no basic medium that can help you to release this. Otherwise the reaction could have taken place and can have formed the reaction. The reagent required one. Water comes and attack on the carbonyl carbon. One of the nitrogen acquire one more hydrogen from here. Carbon is now attached to OH group. COHs have been formed. In the very next reaction, this reaction departs RNH2. RNH2 is the amino. Okay. We've got this reaction mechanism, fine, and it's a simple reaction that we can follow. So learn the simplest way to write down this reaction, that RC double bond OH on reaction with hydrozoic acid. This is it, no? Hydrozoic acid and concentrated H2SO4. We also have the concentrated H2SO4 acidic medium. So this will eliminate out CO2. It will simply give you RNH2 plus ammonia gas is eliminated out, not ammonia. This CO2 gas is eliminated out already, and then another thing that was eliminated was the nitrogen gas N2. This is how the reaction takes place, N2, CO2 and RNH2. That is the simplest way to learn this reaction, just to learn now this reaction. Done. So now we'll move forward and I'll take you to the carboxylic acid derivatives also. So now from here we'll reach to carboxylic acid derivative. The reaction of benzoic acid with hydrozoic acid in presence of H2SO4 gives what? Reaction of benzoic acid with hydrozoic acid. Oh, benzoic acid is what, guys? This is your benzoic acid. On reaction with Schmidt reaction, hydrozoic acid. Also concentrated H2SO4 is there. So this makes the reaction go in forward direction. Simply it will be connected to NH2. CO2 will be eliminated out plus nitrogen will be eliminated out. So now check the correct answer. I think aniline or benzamide and phenyl cyanide. Only aniline is correct. Although what we are getting right now on the attack of ammonia, we can reach it, we can make it reach to the benzamide or benzyl cyanide, but not from here. Next question, please. The next question says the laboratory method of detection of the carboxylic acid. How can we detect whether we are given up with the carboxylic acid or not? So we have one very important method called as bicarbonate test, or we also call it as hydrogen carbonate test. So carboxylic acid react with weak bases such as carbonates and hydrogen carbonates to evolve carbon dioxide, and this reaction is used to detect the presence of carboxyl group in the organic compound. So this is how the reaction occurs. RCOH, which is acid, NaHCO3, which is basic in nature, reacts and makes RCONa, as a salt plus water plus CO2. CO2 gas eliminates out with brisk effervescence. So brisk effervescence confirms the presence of an acid or COH group. Also, strong acid plus strong bases make weak acid and weak base. So the compounds which are more acidic than bicarbonic acid, they will only give this test positively, and only a few other special cases like picric acid, squaric acid, etc. also give this test. Phenol doesn't give this test. Phenol never gives this test. Alcohols don't give this test. Then a question is here, which derivative of phenol gives effervescence without sodium bicarbonate? Which derivative of phenol gives effervescence with sodium bicarbonate? Orthocresol, catechol, bromophenol. Yes, trinitrophenol, which is called as picric acid. So guys, we have now preparations of the acid derivatives, because till now we have completed everything related to carboxylic acid, and now the time comes for its derivatives. So the derivatives are, sir, can hydrogen also be termed as effervescence? Do we guys understand the meaning of effervescence? Effervescence is just a practical, what I can say, observation. It's a practical observation. Have you ever observed while you open a bottle of soda, like cold drink? Sometimes we open it and the gas, CO2 gas, dissolve in it, comes out with a brisk effervescence, hissing sound. That is called as brisk effervescence. Hydrogen doesn't come out as brisk effervescence, but hydrogen being a good fuel, sometimes when we light up over the surface where from water it is coming up in the form of bubble, the bubble bursts and produces sound of like pop sound. So hydrogen comes up with the pop sound. Brisk effervescence is something else which comes with the CO2 gas, this hissing sound like that. Okay, we'll plan. Now we'll come to the preparations of the derivatives. The very first derivative we know, that is your none other than acid chloride. We also call them acyl chloride, RC double bond O Cl. So guys, how can we prepare it? We have plenty of methods to prepare them via SN to TH reaction mechanism. So we have some important reagents with us, this one and this one, where it is the most preferred one, because whatever the reagent, like whatever the byproduct we are getting are gases, and gases will eliminate it out, leaving behind the one which is needed in excess of the amount. Another reaction could be like next is acid anhydride. We all know what acid anhydrides are and how acid anhydrides are prepared, just by providing the dehydrating agent to an acid. Two of the acids are combined together, one of the water molecule is condensed out, the remaining one will be your acid anhydride. Whenever you apply or you put water inside an acid anhydride, it will again create or cause you the same acid from which it is made. Anyways, I'll show you some reactions here. There's a dehydrating agent we have. So dehydrating reagent works in acidic condition, and water is eliminated out, producing acid anhydride. In the very next reaction, we are getting reacted with pyridine. So how does pyridine look like? This is your pyridine. So guys, pyridine with its nitrogen can attack on no, nitrogen it is not attacking. What we are doing is simply we have one acid halide with us. This acid halide is getting reacted with an ester in this way, where let us suppose this O is coming here and then Cl is departing. Then HCl will form. Pyridine is helping in what? Pyridine is basically wherever the excess HCl is formed. So this is what consuming HCl as byproduct. It consumes the HCl which is prepared as a byproduct. So there are plenty of ways now, because we all know that SN2TH is the fastest rate of reaction for acid halide. So anything can be prepared using acid halide. Now let us suppose if we have a question, 2 moles of acetic acid are heated. It's very simple here. Acetic anhydride will be the product over here. But anyways, we will come to a good question now. And like acid which doesn't form an anhydride when treated with P2O5 will be. So what do you think, which cannot give you this one? Acetic, benzoic, formic. So let us suppose if we talk about formic. Isn't it? What do you think? And propionic also gives, acidic also give. Okay. Maybe benzoic doesn't give because this reaction mechanism, maybe SN2TH. Formic is the only correct answer. Let me see. We didn't get any of this concept till here. So wow, I'm ready without sleep. That is good. Great of you. Okay, I got it, this part. So guys, this reaction doesn't work like this, and instead what happens, out of just HCOH only, this is something that we have to all take care in our mind. Just put a note here, and here's a note that HCOH plus P2O5, which works as a dehydrating agent, on heating eliminates out CO2 out of this and also forms H2O, and doesn't form anhydride, does not form anhydride. Rest all do. Doesn't form anhydride. So formic acid is the correct answer here. Then we have esters. How to prepare ester? It's simply esterification is the reaction, we all know. Till now we also have covered this part. OH from here, H from here, ester is formed, and we have also covered its mechanism. This is called as Fischer esterification, the reaction, or this is called as Fischer esterification. So the RDS of the reaction is nucleophilic attack of alcohol on the protonated carboxylic acid. Very easy, yaar. We already have covered this part, yaar. This is SN2TH mechanism, everybody. Or you can simply take into this way, like R, C double bond O, OH is there under the influence of acidic hydrogen. Although the hydrogen comes over here, rearranges itself, and finally, this is how it look like. This is OH2 positive. This is now a good leaving group. And then comes the nucleophile with R dash OH. This dash OH comes over here. The electron density shifts like this, comes back like this, and this departs. So with the elimination of H2O, we receive R C double bond O, ORH, and then departs your, the acidic catalyzed mechanism was here. Initially used it, later on removed it. OR. So that's what our ester is. An sp2 hybridized carbon changing sp3 because of the formation of the, you all know what I'm talking about. This is your SN2TH reaction. So preparation of the SN is nucleophilic substitution, and TH is through tetrahedral intermediate. The tetrahedral intermediate has sp3 hybridization, and that's why it has been said that because of the sp3 hybridization there is instability due to increased repulsion. So R should be smaller in order to carry out this reaction. And esterification in backward direction is also called as hydrolysis of ester. Hydrolysis of ester, or we call it saponification. Saponification. Then we have the small size of R in acid and alcohol decreases the crowding in transition state of RDS. We know, yaar. Move forward here. One of the question is given, what is the correct order of rate of esterification here? We know that higher is the alkyl group attached, or bulkier is the alkyl group attached, lesser will be the rate of reaction. Fastest rate will be shown over here by formic acid. So the correct answer should be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, like this. C is the correct answer. And one of the most easy question we have seen. Then is preparation of ester from another methods. No, we have covered this part earlier, right? Oh yeah, other derivatives can also help you to prepare ester, such as RC-CL. I told you it's very easy reaction. This will come, attack here, it goes up, it comes down, and then removes the leaving group like this. This is also happens with the SN2TH mechanism. Similarly, is acid anhydride. You come here, you attack here, and make this part leave. RO minus will acquire its H, will acquire ROH, and then ROOR is the ester. Next is one reaction. We already have studied this reaction in our previous chapter of aldehyde and ketone. The reaction says Baeyer-Williger oxidation. The reaction of a ketone in the presence of peroxy acid or peroxides and an oxidant. So guys, you all remember this is how it is formed. R1 C double bond O R2, but this, how come this R2 is attached here? So this has been decided by R2 has higher migratory aptitude. The one which has higher migratory aptitude will be attached with the oxygen. Let me show you the mechanism. So how does the mechanism work? Initially from the per acid, this oxygen acquires one hydrogen with a positive charge, then remaining this O negative attacks on this carbonyl carbon, and then oxygen again reaches to ROH. See, this is it. This is the carbonyl carbon with R1 R2. One is group is OH, another one is this whole group. This whole group is here. Here it was R3, here it is oxygen already present there. So in the very next reaction, this peroxy bond breaks down and makes, now see, this is the important part. R1 is attacking here. So R1 has the migratory aptitude. One of the alkyl is participating eliminating here and attacking on the oxygen, that actually makes it OR group. R2 already is there, OH is already there, hydrogen will be eliminated out, it becomes R double bond OR. So this is the migratory aptitude. So let's say if I give you the same reaction, and if I ask you the same reaction in case of so many reagents, such as, take this example with me, we have HC double bond O CH3, and now we are treating it with metachlorobenzoic acid, which is MCPBA, which is another per acid, and then we have CH3C double bond O C2H5 with MCPBA, and then one more reaction is there, benzene is here, C double bond O is here, CH3 is here, again MCPBA. So the question is how can we make the final product, and how to decide that what product has to be the major one. So this is I want to teach you. This is how we can identify which one will be the major product, by simply finding out that step in which alkyl group was attacking on the oxygen with higher migratory aptitude. So the one which is having higher migratory aptitude will go and get attached with the oxygen, and that is what I want you people to learn. Not just the whole mechanism, not required. Just stay focused on what I'm teaching you. Give me a sec. Applying the charger here. So come back. This has the higher migratory aptitude. Here this has ethyl migratory aptitude. This has this benzene. So this will give you CH3, not this, HOC double bond O CH3. Because hydride has more, what I'm telling is, it has to the alkyl part, no? R is attaching to the OR. OH has been attached here. Similarly, it will give you C2H5 O C double bond O CH3, and this will give you these are the products. Then we have another preparation from the silver salts of carboxylic acid, and that give ester. So this happens where we usually take bulky R here. So let's say this R is a 3-degree alkyl group. If this R is a 3-degree alkyl group, then RC double bond O OAG, and then we are having Cl2, or let's say Br2 CCl4. Then this reaction gives you RC double bond O OR plus AgBr, and now the reaction becomes Beerbohm-Simonini reaction. This is called as Beerbohm-Simonini reaction. Rather than calling it as the Huns-Deiker reaction, it becomes this. So guys, let me take you to one example. Maybe you will be getting it very easily, and after one example you will be getting me what I'm trying to explain you. So let us suppose we have CH3 CH2 C double bond O OAG, silver salt of this, and we are reacting it with Br2 CCl4. the product will be CH3, CH2, C double bond O, and no, not like this, CH2, then this is CH2 Br plus CO2 gas eliminated out, elements out, and AgBr is another product settled here. This is one reaction. Now the same reaction if I carry out in the presence of some 3 degree, let us suppose we had alkyl group here which is connected to COAg. So what happens in these reaction? Well, this radical is actually a bulky radical, and bulky radical doesn't give you a stable, not just about stable, but it's all about the attack on the another species. So Br2CCl4 under this reaction gives you CH3, 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 C double bond O radical was there, and then it makes you maybe I have taken it incorrectly or what. Yeah, I have to recheck it here once. Give me a sec, guys, give me a sec. Birbom Simonini is the name of this reaction. Birbom Simonini. Okay, with iodine it happens. Got it. My bad. So with iodine, that might be because iodide radical doesn't make the bond very easily that we are trying to make. So that might be a way. So pardon me, everyone. Let me come over here. Let me come. So this is not about alkyl, but this is all about I2 in the presence of iodine and CCl4. This reaction becomes Birbom Simonini. Now let me show you the mechanism. So if the same reaction we want to carry out, the one which is given over here, if the same reaction you want to carry out, same reaction as in, let's say CH3, CH2, C double bond O, OAg, then in presence of iodine, the reaction will give you a different product, that is CH3, CH2, C double bond O, OCH2, CH3, which is an ester, not an alkyl halide. Plus no CO2 is eliminated out, only AgI will be formed here. So try to understand. The above reaction is called as Huns-Diecker reaction, and this reaction is called as Birbom Simonini reaction. The spell might not be correct exactly, but we have this name, and I searched the same name and then I came to the final conclusion after this reaction. So guys, please learn these two reactions, highly important. And allow me just a minute, I'll come back after a couple of minutes with water. So did anyone try? Like hopefully you've gone through these reactions and now you understand the difference between using iodine or chlorine or bromine there. So fluorinations are highly exothermic reactions. We do not carry out fluorinations usually like this process. There are some separate process we already have gone through for the preparations of RX, and that are typically different reactions. But here in this reaction we have some different product which is coming out of the reaction as an ester. The last portion of this entire chapter is the preparation of amide, and then we'll come to their common reactions, and then we'll wind up. Amide can be prepared using so many different processes. The very one of them is SN2TH reactions and eliminating out ROH, eliminating out ROH out of it. Sorry, it's carboxylic acid. So initially we'll be eliminating out water out of it, and then NH2 will be connected over here. Then another reaction could be NH3 attacking there, Cl is departing. Amide, you can also make this is like 1 degree amide we had. This is primary amide. So using same process we have prepared secondary amide. So like that you can do. So always remember that 3 degree amines cannot undergo the reaction. There is no reaction with 3 degree amine, and because of their bulky nature they do not undergo SN2TH mechanism very clearly. And as I told you that the mechanism required for this reaction is they form simply RC double bond O R3NH positive negative, simply salt, a quaternary salt is there. That doesn't undergo any further reaction because this cannot undergo SN2TH because of its bulky nature. Then we have imide formation, guys. Imide, you know imide, what is imide? Imide is actually N, like earlier we were studying about C double bond NH2, that was we used to call it amide. So now if somewhere is like we are getting C double bond NH, right? C double bond, what is imide yaar? Oh, this is imide actually. C double bond NH and then another connected to C double bond O. So imide formation may take place in this way, like we had succeeding anhydride first, 2 equivalents of NH3 prepared this molecule, and from this itself water elements out, formation of succinamide take place. Similarly, we have nitrile formation. Nitrile means cyanide formation, which is also, I told you, one of the we also can call amide, this cyanides as derivatives of carboxylic acid, and by dehydration, simply dehydration of amide you can produce it. Now we'll try solving some questions and then we'll lead to the some other remaining reactions of compounds. So we have CH3Cl which attacked by KCN. So A will be CH3CN. Hydrolysis, it gives you CH3COH. This gives you an amide, like this is giving you CH3CO minus NH4 plus, and then further on heating is gives you CH3CONH2, not CONH2, CH3CONH2 amide, metheth. So this is your acetamide, or you can also call as ethanamide. Then we have last and final topic, which is some reactions, and all of them show the similar kind of reaction, which is majorly it will be SN2TH reaction. So let us start it with, there are some reactions. This is RCOCl. If you are producing hydrolysis, then it will give you the acid itself. If you are using alcohol, then it will give you ester. Getting me? यार font छोटा करो यार. This gives you acid, then it is giving you ester with alcohol. If you use pyridine and RC anhydride will be given. This will give you acid anhydride. Then in case of R2NH, it will give you NN dialkylamide. Then we have R2CuLi, which is called as Gilman's reagent, and it provides good source of R negative, so it will create ketone. The similarly RMGX, a good source of R minus, will create a ketone, and R2CD, a great resource of R minus, will create a ketone. The only difference is the reaction stops here. The reaction stops here with R2CD, but this another R2CuLi can produce the R minus, and this reaction can go to the preparation of like this, and it will lead you to the final formation of alcohol. The final product comes up as an alcohol. We have another reaction where RMGX is used. The same reaction will go on RMGX, which is a good source of R negative, will lead out to this reaction and will form CR dash. Then this becomes R dash, and this will become OH, and this is another alcohol we are getting. But the only beauty of this compound, dialkyl cadmium, is that it stops the reaction till here only, and that's why we use this process. Earlier also we have discussed about it, that R2CD is a very important reagent that used to prepare the aldehydes and ketones, and it stops the reaction somewhere. It doesn't, it gives you the selective product, doesn't let you to produce the ultimately alcohol. That is being seen in the case of Gilman's reagent and Grignard reagent. The very next reaction we have, everyone. So the very next reaction is this. Anyways, so what we are doing is, we are simply reacting it with PDBSO4, and this reaction is called as Rosenman reaction. You might have heard of this reaction. It's another important reaction, stopping the reaction up to an aldehyde. So the product of Rosenman reaction is aldehyde, and this is also a selective product we got, not reducing it up to aldehyde to alcohol. It is just stopping the reaction up to aldehyde only, and that is why we use Lindlar catalyst, and which is H2PD, but with BaSO4, which is working as a poison to reduce down the activity of palladium. And then we have LiAlH and trimethyl, anyways, whatever it is, yeah. This is your tertiary butoxide. So tri-tertiary butoxide, lithium aluminum tri-tertiary butoxide in ET2O reduces it to give you RH, like the same aldehyde. Similarly, ARH, and then in presence of AlCl3 also gives you RC double bond O AR, and then LiLH4, NaBH4 gives you the finally 2 alcohol. There is a question, everyone. Try focusing on this question. In this following reaction, the product P will be what? This is Rosenmund reaction. And we all know the product of Rosenmund reaction is RC double bond O H. Aldehyde is the product. Another reaction when RCuCl and AlCl3 Friedel-Crafts, then what is the electrophile? So C, check it out, everyone. RC double bond O Cl with AlCl3 produces a complex of aluminium, which is AlCl4 with a negative charge, along with RC double bond O positive and electrophile. This electrophile is resonance stabilized like this. Complete octet is here with a positive charge like this. Acylinium ion, acylinium cation. This is C is the correct answer. Next is if we are getting this anhydride reacted with NH, exactly the similar reactions are happening. Most of the reactions are following SN2TH reactions only, as you all can see. So R2NH will give you an attack over this. This will be eliminated out, and this is how the product is formed. Then R-OH will give you an ester and converted to R-OH if present in excess. Okay. Then in water it gives you simply acid anhydride to that particular acid. Another reaction could be RMGX. R minus will attack as a reagent and R will be added here. Ketone will be the final product. Then similarly ARH hydride will be taken. AR minus will attack there, and this is how the product will be formed. Okay, so sorry, H minus will go there. AR positive will be attacking there on the no man. AR negative is attacking there. H is going as a H positive. Then PCl5, we have PCl5 or PCl3, we have seen the same reaction. Cl actually minus as a nucleophile we can act upon, and then Cl will be the product, and the same happens in the case of LiLH4 or sorry reducing agents. This happens. These are the reducing agent. LiLH4 under 82O, it reduces down directly to the alcohol. Then we have Friedel-Crafts reaction, and very easy reaction, so you will come to know about it. So how does this reaction work? Anyways, I can tell you how this reaction is taking place. So guys, ARH, what we are talking about was the benzene. On benzene we are supposed to attack with an electrophile. So let us first make the electrophile. So how is electrophile make? CH3 C double bond O C double bond O CH3. So initially we had this AlCl3 with us, that makes a complex AlCl3 along with OCOR, or let's say if it's CH3 then CH3, and with the negative charge, and also gives us an acylinium carbocation as a electrophile. This electrophile comes in attack. The attack is always shown like this, everyone, negative to positive. Anyways, the final product will be an electrophilic aromatic substitution. Substitution product will be acetophenone, and plus H plus is leaving out. Now this H plus might react with that reagent to giving you the acetic acid. Then we had one more reaction called as Perkin reaction. You remember Perkin reaction we covered in the previous class. In the previous lecture, aldehyde and ketone, we had this reaction with us, Perkin's reaction. So how this reaction operates, let us see. This CHO with the anhydride under the presence of acetic acid and its salt under heating produces the cinnamic acid. Cinnamic acid is this. So let me just give you this shortest route of the reaction and how can you know the product formed. Let me just give you the way. So everyone, we have a benzoic acid with a benzaldehyde with us. You already have come across these condensation reactions. It is exactly equivalent to the reactions which you were earlier studying, like aldol condensation. So take this example with you. CH2, we are bringing one CH over here. We have C double bond O, we have O, we have C double bond O, and we have CH3. So now what happens in this reaction? This H2O is eliminated out, and this group leaves behind like this, giving you a final product like this. CH double bond, CH single bond, C double bond OH, and with it CH3 C double bond O and OH under acidic conditions. And as we have seen this, there is already given CH3 COH. So cinnamic acid is one of the product. This is called as the cinnamic acid. So one of the important reactions of benzaldehyde. And now why we have come to this reaction? Because it's a part of anhydride is involved here. This is your acid anhydride. And because of this acid anhydride, we are studying the perking reaction. And we already have covered this part in aldehyde and ketone in the previous chapter. But this is an important reaction, guys. Great. Now we have what is the final product formed in the following reaction. So the reaction has been given to us. This is nothing but a reducing agent. A reducing agent does what? Reduces the given anhydride to alcohol, directly leads to the formation of CH3 CH2OH. Then it will become this, right? CH3 CH2OH is the final product, C. So finally, reactions of esters we have, and probably the final topic of the day, everyone. I have already considered so many suggestions you're giving to me. Thank you, guys. But this is not what we are targeting for. Rupesh Vani. So we have an ester with us. An ester on hydrolysis gives an acid. An ester on reaction with water gives you the salt of an acid, which is called as saponification of the soap. Sodium and potassium salts of the fatty acid. This is under basic conditions it is giving, under basic conditions. Okay, and it's a reversible reaction. Under R attacks over here and gives us the ketone. Then LiLH4 reduces it to alcohol. Other reactions, sodium in this, another reducing agent. Sodium, whenever any metal, acid, metal, alcohol, metal, base, anything is given that behaves as a reducing agent, because we all know metal reacts with an acid producing H2 gas. H2 gas is reducing in nature, and you can see that over here sodium in ethanol gives you reducing, its work as a reducing agent and reduces it to alcohol. Similarly, R2NH is one of the nucleophile and attacks in the SN2TH manner. SN2TH manner, it produces N-substituted amide, N-alkyl amide it produces, which is here N-dialkyl amide with an alcohol as a byproduct, that R-OH. PCl5 does the same thing as the PCl3 does, which is the production of RC-Cl. And then we have R-OH. Oh my God, what does it do? Okay, it's called as trans-esterification. No doubt it's a reversible reaction, because it all depends that the attacking group must have higher nucleophilicity and the leaving group must have a relatively stable leaving group ability rather than the attacking one. So that is called as trans-esterification. So let me just take you to this example that if we are having CH3 C double bond O CH3 OCH3, this is an ester, and here OCH3 could behave as a leaving group if C2 H5 OH is being given, and let's say we are maintaining the conditions into acidic condition. So now what will it do? It will prepare CH3 C double bond will remain as it is, and it will be attached with OC2H5OH. The another alcohol will become CH3OH. This is how it works, guys. We have Claisen condensation here. Claisen condensation. So Claisen condensation is another important reaction in which RCH2 COC2H5 is reacted with OC2H5, and we have seen these reactions earlier. We have seen such reactions some time back. Claisen condensation. So what happens here? Okay. So this is a base actually. This base first attack on the acidic hydrogen and makes RCH negative C double bond O OC2H5, and now it is working as a nucleophile, and then it attacks on the another equivalent of the same RCH2 C double bond O C2H5. And how this reaction works? Let me just check here. Actually, it got slipped out of my mind. Actually, let me just revise this. Claisen यार कैसे खदेरे बदला घिरे हेरे में हक लिए शराब जो मेरे सीने में है, कोई बताए कैसे तुम्हें, तेरे बिना हम कैसे जिए हो सच धीरे, कैसे कटे दिन रात, कैसे हो तुझसे बात, तेरी याद सताए रे ओ सजनी रे, कैसे कटे दिन रात, कैसे हो तुझसे बात, याद तेरी याद सताए रे. Okay, I got an idea. So how am I supposed to do this reaction? This will react on this. We know SN2TH reaction, we are expert in it, and this is also OC2H5. This departs then, so the product will be RCH. Then this had C double bond O OC2H5, and here it has been now connected to C double bond O. This is your product. So this is exactly the same only, and whatever the departed product is there, it will acquire hydrogen from the solvent and will become ROH. This is how it works. So anyways, now let's come to some questions. We have one question here, everyone. Ethyl ester is reacting with axis of the CH3-MgBr. You know what is an ethyl ester? So ethyl ester is CH3 C double bond O or OC2H5, right? So and then when we are getting it attacked by excess of CH3 MgBr, so it will definitely take its 2 equivalent. Why am I saying it 2 equivalent? Because the very first equivalent will go and attack over this position to remove out the SN2TH portion. So this will give you CH3, then it becomes C double bond only, the leaving group will depart and one CH3 will be attached here. So what has eliminated out? This has been eliminated out, OC2H5. Okay, in somehow anyway, so this has been departed. Now the second equivalent will come. So we will use another CH3 MgBr and another equivalent will be used. This is the one equivalent we are using, one more equivalent we are using actually. So this will go and attack and it will do nucleophilic addition reaction. So one of this will be attached here and this will become O minus Mg plus Br and this will be CH3 one more. So right after this, if you go for the hydrolysis, your O negative will be converted into OH. Now can you find the correct answer from here? Can we see some answer? So we had this 2 CH3, 1 C2H5 already been there. Now isn't it there? I guess all of them will be CH3 only because ethyl ester is, I don't know what is ethyl ester. Ethyl ester. I guess this is our product, right? A. See, 3 CH3, 1 OH. 3 CH3, 1 OH. So another question, everyone. So what are the organic products formed in the following reaction? So we had C6H5COOCH3. First is LiLH4, second is hydrolysis, and yes, this will be converting into simply to alcohols, and this will be your CH2. No, this will be CH. Oh, first of all, let me draw what is it exactly. C6H5, C double bond O, OCH3. One product will be this will give you CH3, CH2OH plus one will be CH3OH. Now find the correct answer, everyone. So this is C6H5OH. No. C6H2OH. I think A is correct. A is perfect. Then we have reactions of amide. How many things have been left, yaar? Didn't I cover them all? I did, yaar. Okay, 1, 2, 3. So many things are there, man. I will do it. So guys, reactions of amide will like have a look over here, but definitely we'll finish this part in amines chapter, which is our gonna to be the next chapter apart from here. So in amines we'll cover whole amide portion, and we have some important reactions. One of them is Hofmann bromamide reaction, very useful reaction that actually is helpful to synthesize amines, and one less carbon atom has been reached out of the product. That's why we also call this reaction as Hofmann degradation reaction. So we have amide, and amide has similar kind of reaction. Hydrolysis of all the derivatives produces an acid. So this is the respective acid we are talking about. And another thing, that whether we are treating this reaction in basic medium, it will give you the salt of that carboxylic acid in RCO minus along with the evolution of ammonia. Then we have dehydration of amide. So amides upon dehydration will give you what? I guess they will give you imide. No, sorry, yaar, nitrile they will give. Sorry, my bad. So whole body is like jammed. The amide heated with POCl, P2O5 or SO2Cl2 or POCl3, and the product will be cyanide. Then we have Hofmann degradation reaction, guys. Why am I not telling this reaction or teaching this reaction right now? Because we have a very big chapter to come up with, and where I will explain every single part. Why am I not explaining right now to you? Because not required as of now. Just take the idea how amines are formed from amide, and we require 1 degree amide. We require just what? 1 degree amide only, and 1 degree amide produces a 1 degree amine. That's how we do. So take an idea, like 1 Br2 and 4 NaOH are used in this reaction. I'll show you in its mechanism where and why we are reaching 4. We are reaching 4 NaOH. So first NaOH is coming and making this amide as just accepting this H and getting it converted into N minus. So later on this N acquire Br produces NBr, N-bromamide. So this is actually your N-bromamide, and then after that we are getting it attacked by another base. We had one base here, another base is here, and it occurs this negative charge nitrogen again attacks on one more bromine and makes a, what is it making here? Nothing, man. So rearrangement takes place in such a way that alkyl then attacks on nitrogen where Br departs, and this is the main step. This is the main step where we are getting alkyl and alkyl. The name of this is N-alkyl isocyanate. This N-alkyl isocyanate then combines with HOH and produces CO2 and RNH2. Okay, so this is another kind of arrangement reaction is there. So OH minus comes here, attacks here, and anyhow this time it leaves like this, Rn minus, and Rn minus acquire from this and it becomes RNH2. Or you can do one more thing, just give it hydrolysis. The hydrolysis product will be RNH, and then we have C double bond to OH, and then the another attack may take like this. So one of the CO2 will be eliminated out along with this. So that's it, everyone. Let's try some of the questions on amide. We have an organic substance A that upon treatment with NH3 gives us B, and on heating it C with Br in the presence of, this could be Br2, in presence of KOH it produces ethylamine. So what could be this compound? So this is no doubt on treatment with NH3 it gives B, and which on heating gives C. We treated with Br2 in presence of KOH. So first of all, the compound should necessarily be a carboxylic acid. Let us imagine this is the carboxylic acid under influence of NH3. This will give you an acid-base reaction, CH3CH2 CO minus NH4 plus. This substance upon heating releases out or like kind of produces C double bond O NH2 along with water, right? And then this in reaction with Br2 NaOH, which is Hofmann bromide reaction I just told you, will give you a final product of CH3CH2. Simply CO2 will be eliminated out, and you can directly make the product NH2. So ethylamine is the product. Is the product ethylamine? Yes. Then we were guessed it absolutely correct. We guessed it very correctly. That's the product. That's the answer. B is the answer. So hopefully you all have enjoyed today's session, everyone, and try solving some of the questions by your own. Like these are the questions for practicing. Like we all know the reaction, what it will go and what the product will be there. Answers have been given. Try them by your own, and that's it for the day. But please don't forget to appear in all India mock test for IIT JEE 2025 held by Unacademy, where we are giving exactly JEE Main 2025 type feeling to you. You can really experience the environment and the testing of yourself, and then questions are as per the latest curriculum, and also you can predict your test rank. That will be the thing that will lead you to stand on some point where you can decide by your own that where do I exist right now, where what I have discussed, what I have studied till now, what else can I do for my upcoming test or the same test which is going to happen in JEE January attempt. So that's it for the day. Thank you everyone. Thank you so much. We'll connect in our next lecture on Friday. Friday will deal with atomic structure for all JEE Main 2026 aspirant. Will complete our atomic structure, the huge chapter with so many depth of the concept, and then we'll connect in next class 2 days later. Bye bye.